time to work at the end. So our notes today are on maximum and minimum velocity. So let's figure out what I mean by that. To keep an object in uniform circular motion, there is a minimum speed required to keep the object moving and a maximum speed threshold that is needed to keep it moving in a circle. Okay, we often examine these extremes of velocity needed to keep an object in circular motion when looking at vertical circles. For example, if he doesn't swing this fast enough, is he going to be able to keep it in a circular path? No. Okay, there is a minimum velocity required for him to keep that object in vertical motion, in that circular motion. Okay, and we also see that with objects in orbit. You guys saw that in the simulation you did, that there were minimum velocities required to keep it in motion. There was also maximum velocities allowed to keep it in orbit. Okay, and so that's kind of what we're looking at today, are these extremes, these thresholds that you have to have your velocity fall between in order for that object to stay in that circular path. So let's talk about things in orbit, since we've already looked at this in your RA. What is the net force that keeps a satellite in orbit? Gravity. Okay, so we have force of gravity, F sub g. Okay, that is the centripetal force in this example, the force that is pulling inward and keeping that satellite in its uniform circular motion. If I wanted to write a second law equation for my satellite, I could say that its centripetal acceleration equals its net force divided by its mass. Again, that's just my second law formula, F net equals ma rearranged. Okay, but in this case, my F net is Fg, so I could write it like this. Centripetal acceleration equals Fg over m. I also have a formula for Fg that we can substitute in. And so if I plug that equation in, this is my universal law of gravitation right here. Fg equals g times m1 times m2 over r squared. And when I plug that in, I can cancel the mass of that object, keeping just the mass of the source, leaving me with this, which should look kind of familiar because you've seen it before. In fact, we derived this equation earlier in our notes the other day. That was the formula that we got for little g, for gravitational acceleration, which guess what? That's my centripetal acceleration in this case. So if you're dealing with an orbiting body, the centripetal acceleration is that gravitational acceleration, that little g that we found before. So we get to apply this equation to our circular motion as well. Okay, so little g equals big G times m1 over r squared, because it is the centripetal acceleration for an orbiting body. All right, we still need to figure out the minimum and maximum velocity required to maintain circular motion, but we have an equation that now allows us to relate centripetal acceleration and velocity. Okay, this equation we got in our notes yesterday. Our centripetal acceleration equals v squared over r, but as we just determined, that centripetal acceleration is our gravitational acceleration. So we can set little g equal to v squared over r. And if I wanted to determine what that velocity required is, I just need to isolate that variable. If we multiply both sides by r, we get g times r equals v squared, which of course we would then take the square root of both sides, and we determine that the velocity required to keep a satellite in orbit can be found with the above equation. Okay, so the velocity required would be equal to the square root of that gravitational acceleration, that gravitational field strength, multiplied by the radius of the orbit. Okay, so again, we have just derived an equation. This is the one you're going to see over and over again today, by the way, which that's why I said it might seem a little bit repetitive after a while. Okay, but this is the velocity required to keep a satellite in orbit. V equals square root of g times r. But what if you're not given gravitational field strength? Well, what if you're just given the mass of the source? We did that derivation. We could stop our substitution step and not go as far with it, and that's fine too. Okay, and so we could say that that acceleration is equal to big G times m1 over r squared, keeping in mind that that centripetal acceleration is also equal to v squared over r, and we could set those equal to each other. Since they're both equal to our centripetal acceleration, we can say v squared over r equals our gravitational constant times our source mass divided by radius squared. And again, if I wanted to isolate that velocity to figure out what that minimum or maximum is, I can multiply both sides by r, which does cancel r squared and leaves me with just r down here, and then take the square root of that. So if you don't happen to know gravitational field strength, you could derive this equation instead and stop a couple steps ahead of where we did to get to little g. Okay, so again, velocity equals square root of our gravitational constant times our source mass m1 divided by our radius. All of that under the radical. And you can use that equation. Okay, so let's get back to our circles for a minute. The minimum or maximum speed needed is most relevant at the top of a circle, at least in these examples. Thus, we analyze the top of the path. I have two different examples here where I have an object at the top of a circular path. I have my car right here, okay, and we're going to diagram the forces acting on the car. What forces do I need to show acting on my car? Gravity, always a good place to start. We're going to draw gravity straight down. What other force or forces are acting on my car?
No friction.
Okay, we're going to assume no friction for this, but that was not a bad answer. Sorry? Normal force. Okay, so normal force. What direction do I need to draw the normal force based on this scenario?
Left. Up.
Up. Okay, up. So we're going to draw our normal force upward. You'll notice the way that I drew it, my normal force is shorter than my force of gravity, and it has to be because I need my net force to be toward the center of the circle in order for my car to maintain uniform circular motion. I need a net force that is a centripetal force. So I need the downward pointing vector, Fg, to be longer and larger than the upward pointing one, Fn. Okay, so that would be a free body diagram for that. Now let's look at this guy. We did this one yesterday. But where he's swinging the bottle around on the string, again, we're going to have Fg. What other force do we need to draw? Tension, which way? Down. At that point, the string he's pulling down compared to where that bottle would be. So both Fg and Ft are down, and of course that means my net force is toward the center of my circle, okay, because I have a downward net force. Okay, so we have two different ones. Let's just pick one of them to analyze. I'm going to focus on this guy, okay? And I'm going to call this downward direction positive since that's the direction of my net force. It just makes my math easier if my net force is positive. Okay, and so we're going to start by analyzing this. I know, again, because I know F net equals ma, in this case, I know that my acceleration is centripetal, so I'm going to rearrange that equation, and I'm going to say that my centripetal acceleration equals F net over m. My F net here is Fg plus Ft. And so I have my centripetal acceleration equals the sum of my forces, Fg plus Ft, all of it over m. But again, I'm trying to determine an extreme of velocity, a maximum or a minimum. Okay, and at the top, that object must be fast enough to stay in circular motion, and we're trying to figure out what that minimum speed required is. So we're trying to figure out what our minimum net force and our minimum acceleration would be. And the minimum would be if there wasn't any tension at all. If the only reason it stayed in circular motion at that point was because of the gravity. Okay, so I'm going to put a 0 in here because I'm looking for the minimum. By the way, the same thing is true in this scenario with the car. For the minimum for it to stay in contact with the road, okay, or rather the maximum speed it would need, we would have a 0 normal force there because that would be the moment that it starts lifting off the ground. It's the same idea for both of them, okay, and we'll come back to the car in a minute. All right, so I can rewrite it like this. In fact, for both scenarios, the car and this, I can say that my centripetal acceleration equals Fg over m. Again, we're just looking for that minimum to keep it in the circular path, or in the case of the car, the maximum to make sure it doesn't leave the road. Okay, so from here, again, I also know that centripetal acceleration is v squared over r. So I can set those equal to each other. V squared over r equals fg over m. And again, I'm trying to determine that minimum velocity. I want to isolate that variable. We're going to multiply both sides by r. In just a second. Sorry, I got rid of fg first. So I have mg. My m's are going to cancel. Now I'm going to multiply both sides by r. Sorry, I went out of order. Okay. And when I do that, I have g times r equals v squared, which of course means velocity equals the square root of g times r. Again, that should look familiar. That's the same equation we derived just a second ago for the velocity required to keep an orbiting body in circular motion. Same equation here. Doesn't matter if it's an orbiting body or something being swung around on a string or a car trying to maintain contact with the road. We're going to get the same equation in all of those instances. This is the formula you're going to use. V equals the square root of g times r. And you're going to use it for all of those scenarios. Okay, so you get the same equation for the required velocity of an orbiting body as we get for a vertical circle. So use this formula. Okay, and it's the same equation for the maximum speed or the minimum speed. As we mentioned a second ago, this is with the car, we're looking at the maximum speed he's allowed to drive. You guys do know if you drive over a hill too fast, you go airborne. Y'all know this, right?
Yeah.
I know they show it in movies, but people actually do it in real life if they're speeding and they hit a bump that they don't see. Okay, don't do it. It's not good for your car and it's not safe. But that's what this is calculating. Okay, is how fast can you drive before you go airborne? Or here, how fast do I have to swing it to keep it in motion? So we're looking at a minimum versus a maximum, but the equation looks exactly the same. Okay, and same thing is true for my satellite here. That's your formula for all of these scenarios. All right, so let's try an example with my car. The example says determine the maximum velocity a car can have when going over a hill with a radius of 5 meters. Okay, so again, this hill is a perfect arc, perfect slice of a circle. We're going to pretend. Okay, and it has a radius of 5 meters. I've got my picture here. You're welcome to sketch something similar. Okay, but let's start by drawing our free body diagram. And I know we already sketched it, so let's redraw it. We know that we're going to have Fg going downward, and we know that there is normal force, support force from the ground going upward. Okay, and so my free body diagram looks like that. Okay, but again, remember, I'm looking for these extremes of velocity. I want to know what's the fastest he could drive until he goes airborne. So when I look at this, again, it's the same equation. My acceleration, that centripetal acceleration, will be equal to my net force over mass. My net force, of course, is the sum of my forces. Okay, I'm going to call the larger one positive because that keeps my answer positive. But I have Fg plus negative Fn over m gives me my centripetal acceleration. Okay, and if I'm looking for this maximum velocity, at what point would he be airborne? If you leave the ground, what happens to your normal force? 0, right? So we're going to figure out at what happens if my normal force is 0. Okay, so we're going to put a 0 here because that would be the moment that he has left the ground. Okay, so we're looking for that maximum velocity when he has left the ground. So I'm going to put a 0 here. So now I have, again, AC, centripetal acceleration equals Fg over m. Because I have plus 0, I'm going to get rid of that. And again, I also know that this centripetal acceleration is v squared over r. Again, this should look familiar. We just did this. But I have v squared over r equals Fg over m. And again, I'm trying to isolate that velocity. You're going to recognize the equation because those m's are about to cancel. We're going to multiply both sides by r. Okay, and we're going to get v equals square root of g times r. I told you we're going to do this over and over again. It's the same equation. I'm just proving to you that it's the same in each of these scenarios. Okay, you can derive it too. It's not given to you, so you'd have to derive it or memorize it. But velocity is the square root of that gravitational field strength times the radius. So in this example, we're on Earth. It doesn't say otherwise, so we're going to use 10 for our gravitational field strength. The radius in this question of this hill is 5. Okay, that's the radius of the circular path for this car. So we're not going to do the radius of the Earth. We're doing the radius that gave us in the question. Okay, and so the velocity would be equal to the square root of 10 times 5, which is the square root of 50, which is 7.07 meters per second. That means as long as you drive slower than that, you'll maintain contact with the road on a hill of this size. Okay, so you can't go faster than 7.07 meters per second. Otherwise, you will leave contact with the ground, you will have zero normal force, and you'll be airborne. Okay, so that's how you determine a maximum velocity. It's the same process, by the way. I know we didn't do one, bless you. We didn't do one, but it'd be the same process for finding a minimum velocity since we had the same equation. All right, guys, so you have some questions that look pretty similar to that in your playlist for playlist 2. You can choose to work on that for the remainder of the period today. Alternatively, your gravitational interactions RA is due today, so if you'd rather work on that, you can. Or test corrections, because those are due next Monday, as are retests. So if you need to do a retest, please make sure you have finished those test corrections, and please make sure that you come in to go over anything you missed prior to that retest. Your lab binder is due on the 14th, that is next week, and it needs to have all these labs in it. Obviously, you're about to turn in the gravitation lab, but you should have everything else. And your TEKS test is on Monday. There is a review in AP Classroom for the TEKS. It is the same review for the final exam. If you have questions, please let me know.